and hi all. So my name is Jérôme, and with Nischita from Siemens and Alexander from Holo-Light, we'll present to you this ARtwin project, which aims at moving into the cloud a lot of processing related to AR, what we call AR Cloud, developing an AR Cloud platform for industry and construction 4.0. So just very quickly, a short presentation of this project. We do not have only the involvement of Siemens, Holo-Light, and Beacom, but also the partners such as Nokia, who is working on the 5G technology, on the cloud computation, and also CTU, a very relevant academic partner working on the spatial computing, and also QPlan for the project coordination, and Artefacto, who is developing some very nice application for construction in AR. So the main goal of the project is really to develop an AR cloud platform. It means that we want to move a lot of processing into the cloud for AR to address very large-scale use cases. We will demonstrate, and we are demonstrating now, the use of this AR cloud platform for different use cases, and we will show that just after during this presentation. And finally, we have also some contribution in standardization, because we clearly think that interoperability is a key aspect for the adoption of this kind of technologies. So very quickly, what is AR Cloud? And you can see on the left the main functions that you can find in AR technology. You have first the capture, sensor capture to capturing the world. You have the camera, you have inertial measurement unit, and other kind of sensor in an AR device. But you need also to do some spatial computing, so to understand what is the real world surrounding you and to localize yourself. You need also to display some content, some assets, so you need to store them most of the time on the AR device. And you will have also to render this content in 3D with a rendering engine, and most of the time everything is running also on the device. And of course, the rendered image will be displayed on the screen of the AR device. The idea of an AR cloud platform is to move most of this computing into the cloud and to use 5G connectivity to ensure a very quick access to this data with a huge bandwidth and a very low latency. So this is the idea of the project, to develop an AR cloud platform moving both spatial computing, the storage of the assets that will be displayed in AR, and also the rendering part into the cloud. Why? What is the value proposition behind that? What is interesting here is we can address very large-scale user experience, because, for example, what we have to understand is that for localizing and to provide some 3D registration in AR, we need to have a knowledge of the real world, to have a 3D map of the real world, and by moving this map into the cloud, we can imagine to have a very huge map. So it's not a user experience at few square meters, but a very large experience at the scale, for example, of a factory or a construction site. Of course, as most of the computing is moved into the cloud, we can imagine to have very light AR glasses that are much more comfortable at lower price, because finally you just have a screen and you have tracking sensors, and that's all, in fact, on the connectivity. No more processing into the glasses. And like that, you can improve also the battery life of these glasses and spend many hours experiencing AR. That's very interesting. The fact to move some rendering on the cloud, you can access a very huge GPU, and so to be able to display very complex 3D model at a very high quality. And again, we will show a demonstration during this presentation. And finally, you are agnostic to the device, so you can run your application on any kind of device and move finally all the computing into the cloud. So with the same AR cloud platform, you can address iOS, Android, HoloLens devices. So that's a very cool feature of AR cloud technologies. So just a use case, I will let the floor to Nischita to present 2 use cases, and I will come back just after.
Thanks, Jérôme. So yeah, as part of the project, the ARtwin project, Siemens contributed to 2 main use cases. These are the broader use cases that you see. I will go into a bit of details into how we narrowed it down in the next couple of slides. So the first use case is AR-enabled factory worker, where we are trying to help the industrial worker do his or her daily tasks efficiently. And how we can do that is by allowing them to cope with both kinds of information, which is static and dynamic, because on a shop floor site or on a factory site, lots of things are changing constantly. So you have to have the ability to help the worker adapt to this ever-changing environment. The second use case is dynamic production line planning, where we help planning managers, production site managers try to adapt new workstations or new production line areas. And how they do this is with updated 3D map of the factory site and so on. And I will go into details of these use cases in the next slides when I narrow down into the first slide, which is for the AR-enabled factory worker. And here we chose a factory site in Karlsruhe, in Siemens Karlsruhe. And this is where we try to navigate the service engineer, go into a huge factory site and try to repair or assemble the PS2 onto the actuator. So that's this 1 meter long device which they have to find in the factory site, and then they have to get instructions on repairing it. And here we have 3 key features that we focused on as part of the project. The AR navigation, and as Jérôme, I think, will speak about in detail later, how we use the spatial computing map, the ARtwin map, to navigate the service engineer from outside of the factory site into the factory site and at the exact location as to where they have to conduct this repair. And then that is followed by recognition and guidance. So you show a set of instruction panels, and then with the help of overlaid AR information, they're able to do their task. This is also a very interesting use case from one of our factory sites in Erlangen in Siemens. We have manual workers who try to come up with their own workstations, manual workstations, and these are digitally unskilled workers, and they create cardboard mock-ups. The image is a bit small there, but on the top left side, you see a lot of cardboards which are cut out, and this is how they come up with their own mock-ups of the workstations. And of course, we are not allowed to eliminate them. We are allowed to append to their tasks. And this is where we bring in the planning manager who's actually right now doing sketches and pictures, everything in paper. And then they take them to a 3D expert later who converts it into 3D. And this whole process is so iterative. So this is where we want to use ARtwin also to support and try to firstly digitalize the whole thing and try to make it also real-time and updated. I want to speak a bit about the Siemens Holo layer. I think my colleague Alex, in his other talk there, he spoke about what Siemens uses as AR, persisted AR. So Siemens is, as of now, Siemens internal-only platform, which means that right now it's using it for persistent geolocated augmented reality. And here you see a person who's using the Siemens Holo Layer application on the iOS device. By the way, it plays on different platforms as well. They're using to see live data, which is helping them get information when they want and what they want. So it's both contextual and spatial. And here in the video, you'll also see some parts of navigation. I think it's going to come up a bit later. Navigation and guidance. So yeah, exactly. So this is where they are shown a 3D arrow as to where to navigate to correctly. And this, we used this, the annotation service and part of the navigation service also for the ARtwin project. And I think Jérôme will speak about how we combine the two a bit later.
Thank you, Nischita. So let's have the presentation of the last use cases provided by Artefacto. The idea here is to do some default detection on a construction site. So here we can see that the user is displaying in AR the BIM model directly, perfectly registered with the real building. And he can work in the building and move between the real view and the BIM view perfectly registered. What is interesting here is that you can have all the information related to the BIM model directly in AR in the building. And you can see here that there is a default that can be clearly and easily detected because we have a clear difference between the reality and the BIM model. So Here, just a conformity check says that you have an issue here, like that, workers will be able to come back to correct this default. So this is very useful. The conformity check is very quick, in fact, during the construction. That's a very useful tool. So let's move back to a more technical presentation concerning the AirCloud platform. Just very quickly, this is the kind of infrastructure we have set up for the construction site. You can see that here we have a 5G connectivity. So we have 5G antenna here. And we have all the edge solutions, so both the spatial computing, remote rendering, and the 5G connectivity is on the site, and is put just close to the live basement. And here with 5G antenna, we are communicating with 5G CPE, so the receiver. And as we do not have 5G AR glasses supporting 5G connectivity, we need to move back to the Wi-Fi here to connect with the glasses. But this is the idea on everything here. We have an outdoor telecom cabinet design, but we can imagine also to have a flight case. We have it, for example, to put in the factory. And concerning the service deployment, that's very easy. We have all the spatial computing services, the remote rendering services, also the 5G RAN and core services that are stored in a Docker hub. And just based on help chart on Kubernetes, we can easily deploy all the services on a bare metal infrastructure here of server. So yes, again, you can do it whether on the edge solution we propose, but you can deploy the services on your own cloud or edge solution. So let's talk about now the services. And let's start about the spatial computing services. And as you know, in AR, the main goal most of the time is to provide some 3D registration, so to align virtual context with the real world. And to do that, what is done is that the system have to estimate the position or orientation of the device, what we call pose estimation. Question is how to estimate it. How to estimate the pose, the position or orientation of the device in the real space. We can ask the question, how does human locate himself? That's a question I can ask you. Human is using its visual system, and by looking the world, it creates a 3D map of the real environment. I can ask you to close your eyes. You will be able to describe to me this room with a lot of accuracy. Human is using this 3D mental map and compare what is viewing with this 3D mental map to estimate its position and orientation in the real world. An augmented reality device is doing exactly the same. It means that it's using tracking sensor, the camera here, and it will create a 3D map of the world. And based on this 3D map, it will be able to localize itself. You can see this kind of 3D map here, and we call that the SLAM. Now what we are doing is that we are moving all this computing into the cloud. And this is what we call AirCloud for spatial computing. There is one user that is using one device, and he will experience AR, and he will start to create a 3D map of the real world. And another user can do the same thing with another device, and we create a 3D map of the world, and all this thing is down on the cloud, and the map are stored on the cloud. And thanks to that, a third user can connect to this AirCloud platform, and finally provide some images, and automatically it will be localized in this area. And as it's moving, it can update this 3D map shared by all the different AR devices, and it can extend it at the scale of the factory, typically. This is the main idea of an AirCloud technology for spatial computing. Here is a video showing exactly what's happened in the context of the construction site use case. So you see that the devices are transmitting some images captured by the tracking sensor, and you have the pose estimated that is going back to the AR device. Here is the user that display the beam model to detect default, and you see here in the green pyramid the pose that is estimated in real time on the cloud platform, the pose of the user. Like that, you will be able to register. You are able to register and to display the beam model perfectly aligned with the real building. This can be done at the scale of the building because we are sharing a common map on the server, and the server have a huge capacity of storage, so you can have a very huge map at the scale of the server, what is not possible on usual AR devices. And here, this is the first step. So start by creating a 3D map. So you can see here because if you want to relocalize, you need to have a map. This is the first step, creating the map of the building. Of course, it's a sparse point cloud. You don't need to have a very dense point cloud. Sparse point cloud is enough to localize your device. And this is now the capability to extend the map. So here we have a specific service for mapping, and we have another service that will fuse all the map created by the different devices in a common global map to be able to manage large scale. Again, a new extension of the building, and you see that here we can cover a quite important scale and area in this building. And this is the final map. Okay. So you have seen that we are able to create some sparse map that will be used to localize the device and to provide some 3D registration at a very large scale. But we can continue and create some dense map, exactly as what you see here, based on the images captured by the device. And what can be done? We can also do some 3D segmentation of the real environment that have been captured by the camera and tracking camera of the AR device. It is what you can see here. This is developed by the University of Prague, and what is interesting here is that it will be helpful to compare the 3D maps that have been captured corresponding to the reality with, for example, the CAD or the BIM model of the factory to correct it. Because as you know, when we are speaking about digital twin, most of the time this digital twin is updated. It's not updated, it's out of date because the factory is changing over time. Thanks to that, the goal is clearly to correct the digital twin, not in real time, but close real time, and finally to have a digital twin that corresponds to the reality.
Okay.
Please.
Thank you. So about remote rendering. So probably everybody of you knows the issues when you develop for mobile AR or VR devices. They have limited performance, limited GPU, limited CPU. And if you want to create huge and complex 3D scenes in Unity or Unreal and so on, either you have to do a lot of optimization, especially when you have heavy polygon models, you have to do reduction, or if you want to have cool shader effects, transparency, and so on, you need a lot of smart coding. And what we have done to overcome this issue, we outsourcing the computational power, the rendering from the mobile AR VR device to the cloud, to some powerful GPU machine, and this remote rendering stack we call ISOR. It's a two-component solution. We have the server component, which is usually made in Unity or Unreal, where you have the plugin you integrate, and then we have the client component on the extra device side, which is a thin shell application which receives the rendered stream. So 2 images if you have a smart glass with left eye, right eye, or 1 image if it's a smartphone or a tablet. And we upstream all the necessary input data like the SLAM or hand or controller gestures. And this solution provides then the possibility to create huge and powerful scenes, also with very less time to spend for it. On the next 2 slides, I show some examples we have made. For example, here we see a car example where we compare local rendering with the remote rendering. So local rendering means very simple shapes, very simple shaders, simple effects. And on the remote rendering side, we have reflection, we have lighting, we have transparency, and huge polygon models, which would not be possible on the local side. And a second, also very nice example is this one, where we are visualizing point clouds on, for example, here on HoloLens. This is a point cloud model with more than 1 billion single point elements, which we also includingly overlay with the CAD models, which you maybe want to do for planning, for replanning in such a facility, and also design review or other use cases. So if you are interested to test this stuff, then please come to us to Holo-Light private room in the first floor on the exhibition hall. And thank you.
Thank you, Alex. Joe, just a final slide for the conclusion. So what we have to understand is that AR Cloud Platform is a key component for industry and construction, because it can clearly improve the productivity and the quality by providing AR at a very large scale, by displaying very complex 3D model as presented by Alexander. So yes, this is a key component for industry and for the construction domain. If you want to know more about what has been presented during this presentation, you can have a look to the ARtwin project webpage. Concerning the spatial computing, it is based on a framework, an open source framework based on Apache v2 license. So everything is free because we clearly think that AI cloud technology, we need to provide an open source solution. Concerning the remote rendering, do not hesitate to discuss with Alexander, and you have the website here, Holo-Light. And concerning the application shown for detecting default in AR in a construction site, do not hesitate to have a look to the website of CADIVIS. Thank you all. If you have any question, you are welcome.
Yeah, so big hand, first of all. Thank you so much for that presentation. We've also been, we developed our project 3 years ago and made it low poly VR because of this problem, right? So thank you. We'll be looking into this. We have a good amount of 4 minutes, 4 whole minutes for questions and answers, which is amazing. So thank you for staying on time. First question. Yes, I'm going to bring you a microphone, so just hold tight. Here you go.
Great, thank you. Hi there. Just really a clarification, but in terms of the SLAM computation, are you computing the point cloud on the device and then doing some kind of point cloud registration remotely, or are you streaming the IMU and sensor readings to the cloud and doing the computation on the cloud?
That's a good question. Typically, we have to create our own map, our own point cloud, because we do not have full access to the point cloud of existing solution. So we are streaming the images, we are streaming just only the keyframe, and we are streaming the images, we are streaming some other information, and we are reconstructing our own map into the cloud. And based on this own map, we are able to provide some relocalization, so we can send just an image and provide the pose corresponding to the image. And we correct the tracking because we keep the tracking, estimating the pose at a very high frequency, but with a drift, we keep the tracking on the device. And we come here to correct the drift of the tracking based on the relocalization computed into the cloud. So we don't need a very, very low latency solution. That is the case for remote rendering, but for this part, no. Every second, we estimate the pose, and we come to correct the drift of the tracking.
Great, thank you.
All right, other questions? Yes, thank you. Here you go.
Is there any limitation for the size of the building? For example, how many square meters can be supported maximally for mapping the building? For example, if a warehouse or stadium or even, can that be done in one map?
This is a good question concerning the range and the size, on the scale of this kind of technologies. The more is important the size. If we have a very huge area, we need to have a very huge map. But the issue is that we have some processing on very huge maps, such as what is called bundle adjustment. So it's the optimization of the full map with the position of the camera can be very challenging. But what can be done is to structure this map and cut it in different maps, or imagine to have some progressive representation of the map and to optimize it progressively. So there is some solution today. What we plan to address is a stair of a building, and we can imagine to have several maps, and for each stair we just connect to the corresponding map. But yes, having just one unique map covering a stadium, covering a city, it's for close future. Now what we have to do is really to cut this area in different maps to solve it. But we can address larger area compared to what exists today, for example, on existing AR devices.
This can be done only with mobile devices, not with laser scanners.
Sorry, can you repeat?
I'll just repeat the question. It can only be done with mobile devices and not with laser scanners.
Today, we are really focusing on mobile devices or AR devices. The next step for us typically is clearly to integrate this kind of laser scanner to improve the quality of the map. But again, what is very interesting is to be able to update continuously this map. And to do it, for me, the best solution is to use AR devices. Because if we imagine that user will wear some glasses, they will be able to contribute to the update of this map, to have a crowd mapping in real time. So when you are doing a capture with a laser LiDAR, you are doing once a month, once a year, and that could be a very good input that will be updated with the tracking sensor embedded in the AR devices. So this is the main idea. So today we are focusing mainly on RGB, on tracking camera. The next step is also to start the map with a 3D scan.
The question is the platform open for developers?
Yes, for sure. It's on GitHub, on all the, at least for the spatial computing. For the spatial computing, everything is on GitHub, so do not hesitate to have a look to the Solar framework.
The same for the remote rendering.
It's the same for the remote rendering, yeah.
Perfect. Well, thank you so much. Let's give another big round of applause. And we'll just ask you to visit the technicians at the back. Thank you so much for your time today. Thank you. Everybody who's in here, we have another talk coming right up, and this one's off now, right? Yes, good. Okay, I'm just going to leave that there.